Hi, this is Margo. This is Sunday, June 24th, 2018. We're going to continue learning about greenhouse gases as today we start exploring ozone and really what it does for the atmosphere, what it is. There's good ozone, there's bad ozone, there's supposedly a hole in the ozone layer over the Antarctic and over the Arctic. What does it mean? The ozone layer is in a very fragile condition and it's being depleted. So it's another one of the greenhouse gases that does contribute to abrupt climate change and the warming of the climate. So CAMS does track ozone, and here I have CAMS up, and you're familiar with this if you've seen some of my other videos. This is the Copernicus Atmosphere Monitoring Service, and it's from the EU, and they collect data from stations all around the world and then put it together in these databases and do predictive forecasting. But we have actual data back to Wednesday, June the 20th and through Sunday, June the 24th UTC time. So if depending on where you're located in the world, it's already up for your day because they're already on the 25th now. So here is a view of the South Pole, the Antarctic. This is the western Arctic side. Here's the peninsula that goes up. It points, the little tail points toward the south end of South America. And this, we're looking at total column ozone. You can see total column. And when you're looking for the level of good ozone, that's what you want to look for, is total column. So we're going to look at this in more detail in just a little bit, and I'm going to show you how you can go to CAMS and check out the ozone levels all around the world and where you are, and see what the good ozone level is, what the bad ozone level is for your area. And if the ozone layer is thin where you are, then if you go out, you're going to need to have protection because you're going to be getting more UV rays, ultraviolet rays, that can cause burning of the skin and lots of bad things. So we're going to go over all of that so you understand a little bit better about ozone. And here's a global view of ozone. I'm going to go over this too. This is on CAMS. And first of all, we're going to look at how it's read. It's read in DU, and that's called Dobson units. So I pulled up Dobson unit on Wikipedia so that we can understand just very basic what we're looking at. And the Dobson unit, or DU, is a unit of measurement of the amount of a trace gas in a vertical column through the Earth's atmosphere. It originated and continues to be primarily used in respect to atmospheric ozone, whose total column amount, usually termed total ozone, and sometimes column abundance, is dominated by the high concentrations of ozone in the stratospheric ozone layer. One Dobson unit is equal to the number of ozone molecules needed to create a pure layer of ozone 0.01 millimeters thick at STP, that's standard conditions for temperature and pressure. The Dobson unit is defined as the thickness of that layer of pure gas which would be formed by the total column amount of STP. This is sometimes referred to as a milli-atmocentimeter. A total column amount of 300 DU of atmospheric ozone therefore would form a 3 millimeter layer of pure gas at the surface of the Earth if its temperature and pressure conformed to STP. The Dobson unit is named after Gordon Dobson, a researcher of the University of Oxford, who in the 1920s built the first instrument to measure total ozone from the ground, making use of a double prism monochromator to measure the differential absorption of different bands of solar ultraviolet radiation by the ozone layer. This instrument, called the Dobson Ozone Spectrophotometer, has formed the backbone of the global network for monitoring atmospheric ozone and was the source of the discovery in 1984 of the Antarctic ozone hole. So I'm going to leave links below to all the websites that I refer to, and you can read through and learn more. NASA uses a baseline of 220 DUs for ozone. This was chosen as the starting point for observations of the Antarctic ozone hole, since values of less than 220 Dobson units were not found before 1979. Also, from direct measurements over Antarctica, a column ozone level of less than 220 Dobson units is a result of the ozone loss from chlorine and bromine compounds. In addition, Dobson units are often used to describe total column densities of sulfur dioxide, which occurs in the atmosphere in small amounts due to the combustion of fossil fuels from biological processes releasing dimethyl sulfide, or by natural combustion such as forest fires. Large amounts of sulfur dioxide may be released into the atmosphere as well by volcanic eruptions. The Dobson unit is used to describe total column amounts of sulfur dioxide because it appeared in the early days of ozone remote sensing on ultraviolet satellite instruments such as TOMS. Anyway, it goes into all the math. So that's where the Dobson unit comes from. So when you're looking at these charts, so what they said was 100 Dobson units equals 1 millimeter of ozone. Or 300 DU of atmospheric ozone therefore would form a 3 millimeter layer of pure gas at the surface of the Earth. So let's just go back to CAMS real quick. And so if we look at this blue color, here's our chart down here. That's 225 Dobson units, DU. That's where the ozone hole is, or the thinnest part is in the South Pole. And then the next green is 250. Then the more yellow-green is 275. And then the yellowish, and with a little tiny green on it, is 300. And they consider 300 DU to be average. And ozone, the levels change a lot. They change a lot from day to day, and it's the top layer of the atmosphere. It's the very top layer, and it's what keeps the UV rays out. So we're going to go over all of that in a minute, and why it's so important that we understand ozone and what's going on. And what's so beautiful is the Earth actually makes its own ozone from the sun, from oxygen in the sun. It's just, I didn't know any of this until I started looking. And you'll see higher levels of ozone, like in this darker area, like this dark gold, that's 375 DU, and so forth. And so and we can change the area that we're looking at, as you know, here. And then if you want to look at the Arctic, just click on Arctic view. And there it is. And now we're looking down at the North Pole, and you don't see any blue up here because it's heading into summer, and so it doesn't have a hole in the summertime. Ozone is created, there's a lack of ozone in the wintertime when the cold weather. So the South Pole is just going into winter, and it's actually nighttime there, and there's no sunlight, and so it's not going to be making any ozone for the next month or so. This is why we have to do a whole show just for the background, because it's very complex, but we have to have ozone. Okay, now the next website I have up is NASA's Goddard Space Flight Center, and they've got satellite images of the ozone on both the North Pole and the South Pole. Here is the latest picture that they have of the South Pole of Antarctic from June 20th. That's the latest one. And here's their scale down here at the bottom. You can see the green around there. That's about 300 DU, like what you saw on the cams. And then when it starts going into the blue, that's the lesser amounts of the ozone. And 1979, when they found the ozone hole, they had not registered any levels below 220 DU. So that's the baseline. Now, it has been lower than that, but that's like, we don't want it to get lower than that, because that's low. And so you can see it's pretty large, pretty much covering up the Antarctic with that bluish range. It's not really going down into purple, which is good, because that's 100 DU, and then 0 is not good at all. So it hasn't been down to 0, but you can look back through. I'm going to show you some websites where you can go back through and see where it was in 1979, and it was shocking, and there was a big hole at the Arctic too. So you can actually run a movie. Let's run the movie here. It's going to run fast. Now this is from last year, and it's running through really fast down here. And it's showing the see how it fluctuates and moves around? This is the South Pole ozone hole during the winter. And now it's summer down there, and see how it's closed up, because December is summertime for them, and so it's making ozone during that time. You want to see that again? That was interesting, wasn't it? So it's starting in the winter season there, and then it's going to go into the blue, so where it's losing ozone. See, it's getting colder. So you can see the Antarctic underneath there, and it got down to purplish there, and now it's building back. Now it's getting warmer as it goes into December. And so that's from last year. So this is a really cool website, and when you go on down, let's see, where was it? Ozone maps. Oh, that's the page we were on. Oh no, here's ozone maps. And here's starting with June, what it looked like every day this month so far. And then you can click on one and get the big picture and see what it was like there. That was on June 18th. And so forth. So this is a really cool website. Let's go to Ozone Facts so that we can learn a little bit more. What is ozone? Ozone is a gas made up of 3 oxygen atoms, and it's called O3. It occurs naturally in small trace amounts in the upper atmosphere, the stratosphere. Ozone protects life on Earth from the sun's ultraviolet or UV radiation. In the lower atmosphere, or the troposphere, near the Earth's surface, ozone is created by chemical reactions between air pollutants from vehicle exhaust, gasoline vapors, and other emissions. At ground level, high concentrations of ozone are toxic to people and plants. So right there, they just told you what good ozone and bad ozone are. The ozone high up in the atmosphere or in the stratosphere is good, and that's what's created by the Earth. But the ozone towards the surface in the troposphere is what's created by man, by pollutants, and that's bad ozone. Stratospheric good ozone. 90% of the ozone in the atmosphere sits in the stratosphere, the layer of atmosphere between about 10 and 50 kilometers altitude. The natural level of ozone in the stratosphere is a result of a balance between sunlight that creates ozone and chemical reactions that destroy it. Ozone is created when the kind of oxygen we breathe, or O2, is split apart by sunlight into single oxygen atoms. Single oxygen atoms can rejoin to make O2, or they can join with O2 molecules to make ozone, or O3. Ozone is destroyed when it reacts with molecules containing nitrogen, hydrogen, chlorine, or bromine. Some of the molecules that destroy ozone occur naturally, but people have created others. And anyway, it goes on. Ozone in the stratosphere absorbs most of the ultraviolet radiation from the sun. Without ozone, the sun's intense UV radiation would sterilize the Earth's surface. Ozone screens all of the most energetic UVC radiation and most of the UVB radiation. Ozone only screens about half the UVA radiation. Excessive UVB and UVA radiation can cause sunburn and can lead to skin cancer and eye damage. And that's what they're talking about, like the ultraviolet radiation coming through, and even though it might not be really hot outside temperature-wise, you go out and you feel like your skin is burning, the plants are burning, they're not growing the way they should. It's because the UV radiation, it's too much UV radiation because there's not enough ozone in the atmosphere, good ozone, to filter it out. Increased levels of human-produced gases such as CFCs or chlorofluorocarbons have led to increased rates of ozone destruction, upsetting the natural balance of ozone and leading to reduced stratospheric ozone levels. These reduced ozone levels have increased the amount of harmful ultraviolet radiation reaching the Earth's surface. When scientists talk about the ozone hole, they're talking talking about the destruction of stratospheric good ozone. Tropospheric bad ozone. Although ozone high up in the stratosphere provides a shield to protect life on Earth, direct contact with ozone is harmful to both plants and animals, including humans. Ground level or bad ozone forms when nitrogen oxide gases from vehicle and industrial emissions react with volatile organic compounds, carbon-containing chemicals that evaporate easily into the air, such as paint thinners. In the troposphere near the Earth's surface, the natural concentration of ozone is about 10 parts per billion. According to the EPA, exposure to ozone levels greater than 70 parts per billion for 8 hours or longer is unhealthy. Now you want to remember that figure because we're going to be looking at that. Such concentrations occur in or near cities during periods where the atmosphere is warm and stable. The harmful effects can include throat and lung irritation or aggravation of asthma or emphysema. So, that level again was 70 parts per billion for 8 hours is harmful. So this is an excellent website. You can look at ozone maps. You can see the northern hemisphere. We can go to the northern hemisphere. Now you see that looks pretty good, but there's a blue area over on the left side there. They don't really talk about that, but there is some thinning of the ozone layer besides at the poles, and we're going to talk about that later on today. There's the North Pole, and you see that most of it is in the 300 DU range, which is average, which is a good range, and you can see it's even higher, like 400, and the red is like 500, and so that's good. That's good to have. That's filtering out the UV rays up there. But you can see over here, over across, I believe this is North America, there is a thinning there. So we're going to move on from this website. Another very good website is called this one, the Ozone Hole, and this is maintained by a group of scientists, and it's probably the best website that I've found with the most facts about ozone and the history of ozone than you'll find anywhere else on the internet. And you can go to Sitemap, and that's probably one of the best ways to use it, and look around, and it explains where ozone comes from, bad ozone, good ozone, climate change. It shows self-reinforcing feedback loops, Dobson units. I mean, it just goes on and on and on, and I mean, it would take me days, literally days, just to go through this whole website with everyone. So this is a good foundation, and then you can go further. Some of their information is kind of old, but it's a foundation. But that's okay, because we need to know where we came from. We need to know what it was like. Here's the ozone hole. Let's look, 1995. Oh, that's been removed. Well, let's see how well this has been maintained. Okay, so this is... Okay, it's making a movie. Here's the ozone hole in the South Pole. It's making a movie through every year. But they're saying since we cut back on using aerosol sprays and different things that the hole is healing, but scientists now believe that it's going to take more than for it to go away, because there's some more ozone thinning that around the world that they weren't aware of before. So let's go to ozone hole 2017. Here it was last year. Here's the South Pole. Here's the level. This was from September 11th, 2017, and you can see it was this purpley color, or kind of, I don't know what color, pinky purple color, and that was at 150 DU. So that was pretty low, but that was when it was cold. Remember, that was during their winter. And then it went up from there to 200 DU in this blue purple, or 175, and then 200 in this blue, and then 250 in this blue. So it does get lower in the wintertime when it's cold, because ozone is only created, okay, here it is the next month. You can see it changing in August, because ozone is created with bright sunlight and oxygen. And so the Earth actually replenishes its own ozone layer with sunlight and heat. So it's a beautiful system if we didn't interfere with it. So site map. What else was I going to show you here? Oh, I was going to show you ozone and climate change. This shows self-reinforcing feedback loops of ozone and climate change, and why the depleting ozone layer contributes to an increase in greenhouse gases, and back and forth. So I'm going to leave, like I said, the links below to all of this stuff. So it's too much to explain all in one video. But it's all feeding in together, and human activity is help breaking down the ozone hole. An industrial civilization, basically. So I'm going to leave the link below to this website. Oh, volcanic ozone hole. I haven't been there. Let's look at that. Solar cycle and volcanoes. It says an ozone hole could form over the North Pole after future major volcanic eruptions, according to the cover story by a NASA scientist in tomorrow's edition of the Proceedings of the National Academy of Sciences. And that was old. But yeah, volcanic eruptions emit sulfur dioxide and a whole bunch of other stuff that go up, and then they start dispersing into particulates, and then they're carried high up in the atmosphere and basically break down the ozone level. They break it down. So that's why we want to keep an eye on sulfur dioxide too. So let's go back. Anyway, there's the site map for that. Not quite ready for that website. Here's a converter chart. If you want to convert millimeters to inches so that you understand how thin a level this